hyperplane, which is dividing the objects into a set of objects having a different classes. That is what is the definition for hyperplane. Similarly, like a hyperplane, we have some other parameters, like we have one more called as a margin, and another term which we usually come across is support vectors itself. Support vectors. These are the terms which we usually come across in a support vector machines. So already we know what is a hyperplane. Now what is a margin? So in order to, what is a margin means it is defined as a gap or a distance between two lines that are closest to data points of two different classes. So let me show diagrammatically so that you will understand what is a margin. Say the data points which we are taking. So these are the data points of one class, and these are the data points that we are having on other class. So we can say, for example, this is my hyperplane. I drew it little, it should be a straight line, bear with the diagram. So if I'm identifying this is my hyperplane which is classifying these into two different classes, then there will be an imaginary two lines that we can draw passing on either side, which are parallel to both these. I'm drawing little away, but actually they need to pass maybe a line on either side. We should draw two parallel imaginary lines passing through the farthest data points that we have. Say this is another point that I'm having through which I'm passing. On either side, there will be some points which are closest to this hyperplane which we have selected. We are thinking this is the line which is classifying the data points into two classes, isn't it? Now, parallel to this, we have to draw one imaginary line on other side, this side, and one line on this side. How these lines should be are, they should be parallel to the line hyperplane and passing through the closest points that are possible on either side. Hope hope you understood what I'm talking. There might be some point through which is close to this, from this set of data points which you are having on this side. There might be one point which it can be one or more than one point possible, which is close, which are closest to this hyperplane, isn't it? Through them we have to draw one imaginary line. Similarly, on the other side also we should draw one hyperplane which is passing through the data points which are closest from this hyperplane, the selected hyperplane, towards the other side of the class. So that is circle points. I have only one point here. Maybe I have 2 points, 2 or 3 points on the other side. So now these points, when you have two parallel lines like this, now this distance, what we call is, if you think that this is if you imagine that this is like a, if you fold it or make it like a 3-dimensional image, if you draw a, if you convert it into a 3-dimensional, it becomes a cylinder, isn't it? So that cylinder and that outer circumference of that cylinder is passing through these least or the nearest data points that you're having on the either side. Now this radius, what we have, this radius is called as a margin. We call it as a margin, or the total distance is called as a margin, and the width of it is represented with m. So it will be, radius is what we are calling it as the margin. Hope you understood what I'm talking. Did you understand what is a margin? Sir, did you understand what is a margin?
Madam, these are not equidistant.
Yes, madam.
Sir, the drawing I have, because of my bad drawing skills, I couldn't draw parallel, but they should be parallel.
Okay,
You have These should be parallel lines drawn to the hyperplane that we have, which is having a distance or radius. If I'm taking this as a cylinder, the radius of this should be m. That is what is called as a
I understand, madam. Parallel, it is parallel, but the points may not be same.
all points need not pass through the parallel lines. There may be points, there may not be points.
So the distance between this upper
This,
upper parallel point and down parallel point.
that's why I told it's a cylinder. I said when it is a cylinder and a radius, I'm taking it to be W. If I'm taking it as W as my radius or M, which I'm representing here. Now, when it is radius of a circumference of a cylinder, then obviously it is on equal distance on all the sides, isn't it? On both sides, it must be equal distance.
Yes, ma'am.
Yeah, that's what I'm talking, sir.
Okay.
Now, the points through which it is passing. Now, this parallel, imaginary parallel lines, whatever I have drawn, if the data points are falling, any of the one or more than one data points are falling on these imaginary lines, those points are called as the support vectors. You understood? What are support vectors? The data points through which there's parallel imaginary lines parallel to the hyperplane, optimal hyperplane, through which these points are, those are called as a support vectors. Your whole algorithm is based on these points only. That is the main point, sir. See, if you take the same algorithm can be solved using linear regression or other algorithms that we have. If you look at those algorithms, they all depend, all the data points, you have to find the distance and find the like how far they are, or into these are one class, and how you're deciding, you're calculating every distance from every point to every other point. But here in SVM, what we do is we only depend on the data points which are passing through these two imaginary lines. Only based on these lines, you are telling whether any data point that we are having above this line fall into one class, and the ones which are falling below this line fall into the other class. So it's all depending on these support vectors. These are the vectors, support vectors, based on which the whole algorithm is based. That's the reason why that name support vectors came. You understood? There may be 1, 2, or it may be more, but it doesn't matter. On all the data points, we don't consider wherever they are, how far they are. But if they fall after these data points, that means these belong to one class. That's how we work with in this support vector machine algorithm. Did you understand, sir? You want me to repeat it? Sir, in case you are looking at the other algorithms, every data from the distance, when we calculate, if it is k nearest neighbors or something like that, we calculate the distance from every point. We take some distance and calculate and say, since they are all close to together, they form one group. Since this point is away, we say that is another group. That's how we do, isn't it? Even if it is a linear regression or any other thing. But here, what we do in support vector machines is the points through which these lines, these two imaginary lines are passing, based on these points only, we are classifying that any point which is away, which is towards this support vector, these points, these data points which we are considering as the support vectors, based on that, the whole algorithm is working. That's why we are calling them as support vectors. It can be 3 points, or it can be 4 points, or it can be 5 points, but not all the data points we need not consider all the data points. Based on this, we make a conclusion whether which class they belong to. So that's how the name support vectors came. Now this line hyperplane which we have uh, taken, that is again a line. We said, since we said it is a line, obviously it is going to be y is equal to mx plus some c, isn't it? Or if you write in terms of weight vectors, w transpose into x plus some b greater than if it is the hyperplane, we can take it as equal to 0, or the ones which are above can be greater than 0, and the ones which are below can be less than 0. So the equation for this line can be w transpose dot, it's a dot product, no, when I'm talking in terms of vectors. So weight vector transpose dot x into b greater than 0 is the equation. It might be the equation of one line, and the other line will be less than 0 when I'm considering this line is equal to 0. If I consider the hyperplane, if I'm considering it to be equal to 0, the points, all the points which belong above this will be greater than 0 values, and less than will fall into other class. So these two will be the other two line equations possible, these two imaginary line equations. So based on these equations, now you can calculate what is the distance between these two lines. Means the distance between this line and this is one line, and the other line is this line. So what is the distance between these two lines? It need not be 0, it can be 1 also. If you're taking it as a, it is plus 1 and this is minus 1 and this is equal to 1. If I'm taking it, I took example of 0, you can take it as 1 also. Why I took it as 0 is, if I bring it this side, then it will become 0 means minus b it will become. So calculating will be much easier. When I take it as 1, it will be 1 minus b. So, or minus b, minus of 1 plus b will be there. So calculations will take a longer time. It will become more complex. So I took it as 0, so that when I bring on the other side, it will be t transpose w transpose. It will be either greater than or equal to minus b, or it will be less than b. So like that you can take and then calculate. Now the distance, if you calculate between these two line equations, if you calculate, usually it will be 2 by mod of w. The width, the maximum distance between these two hyperplanes, this should be maximum possible. We are trying to identify a hyperplane which whose distance between the two imaginary lines of this hyperplane is maximum possible width. We are trying to identify such a hyperplane. This should be maximum possible width. Like say example, I think in the introduction class also I spoke about this. If you remember, in the first class, when I gave introduction to ML, I spoke about this, but I didn't use the words support vectors and hyperplanes there. Maybe I used hyperplanes, but when I spoke about margin and all, the first topic, I spoke about this. So we are trying to identify such a hyperplane whose the width of that margin should be maximum, and that will be actually 2 by w, 2 by mod of w, because I'm to be the width of or the radius that I'm considering. So how we get that? We have a derivation for it. We can actually solve that derivation. Let me talk about, you want me to see the, tell you the derivation? I can tell you. So if I'm taking that equation to be w transpose dot plus x is equal to 0 is the separating hyperplane that we are looking for. Then the weight vectors of, if you see on one side of the boundary line will be all the positive x's, and the other side will be minus negative x's. So the weight along the line will be weight vector W. So if you are considering it to be a unit vector, then if it is a unit vector, then if you have to make this as a unit vector, then the margin is usually 1 by mod W on one side. Since we have on both sides, it will be 2 by mod of this is how you will get the margin. Is the margin, how do you define, is it's a total distance between the support vectors, so that it is twice that of the twice the distance of between the hyperplane and the imaginary line, or this line. This distance is W, so it will be twice that what we want. Or you can take it as margin M. You can write it as um, if this is maximum possible, or in the other way we can write it as it should be minimum of reciprocal of that should be as small as possible. So to as I have taken that equation, one more equation. If you're taking that equation, that whatever target line which we are considering, if you take it as Ti, if I consider it as Ti into X into Yi is what we are looking for. It's a multiple of the output line, and if it is positive on one side and negative on the other side, so the equation of the line can be written as Ti, that line what I have considered is transpose plus B is greater than or less than equal to 1 is the equation what we are considering. Now this this equation we have to solve, or for each data point we have to check whether that the data point lies on this line or above this line or below this line. Based on that we can decide like whether the data point is a positive, is which is it a X plus or X minus class it belongs to. So to solve that, what we do is we have to minimize it's an optimization problem where we can take the minimum of this equation can be, as I have already written, it is half of W transpose into W. Then subject to what is a, this is a margin what we have calculated. This we want to minimize. Subject to the constraint that this condition satisfies for all I equal to 1 to whatever points we have, all for all the M points, this condition should be true. In such a condition, this value should be minimum. That is what is our problem that we have it now. To solve this, how can we solve this equation is, it's an optimization problem. To solve this, we should use quadratic because it is W square. W square means it's a quadratic programming solutions we have to look for. How do we solve this quadratic programming problems is, we have to find whether if it is convex equation and it has some linear constraints, then we'll be able to solve. So what is a convex problem is, how do you decide whether it's a convex problem or not is, if you take any curve using this gradient descendant, if you take and you find the curve, and if you draw a line passing through two points on this curve, this is 1 point and this is 1 point. Now only 2 points are passing through this line, isn't it? So when it is passing through only any 2 points, and you are able to join them using a straight line, then we say that this curve, this is a convex function, or the line that we have is a convex function, and we will have a unique minimum value or a minimum value for such a problem. So we have to find a curve. If we are able to find the curve which satisfies this equation, and it's a convex problem, then we can say that we have only one minimum or a unique minimum value you can have. So for that we use something called as in mathematics you have optimization problems, you will have another concepts called KKT conditions. Applying the KKK KK means crucial Kunal Tucker or something is there. These are the constraints which we have. Solving optimization problems in mathematics, you have these, sir. So using these conditions, if they're satisfying these conditions, then we say it is we can solve, or we can get the minimum minimum point. So what are those conditions is for which we use Lagrange's multipliers. Let me write the three constraints of these constraints, which is lambda I star. Star indicates that it is for the unique elements or optimal values. T minus Ti into W star transpose into Xi plus B star is equal to 0 is the first condition. And the second condition is 1 minus Ti into W star T Xi plus B star is less than or equal to 0. This is the second equation. And one more third equation is lambda I star is equal to greater than or equal to 0. This is the third equation. So these three are the constraints that we have according to this. These are called as the KKT constraints. So where lambda I is the positive values, this lambda I, whatever we are having, it is a positive value, which is known as a Lagrange's multiplier. It's called as a Lagrange's multiplier. Lambda I, whatever we are having, this is called as a Lagrange's multiplier. L-A-G, Lagrange's multiplier. So now what we have to do is we have to solve these constraints and find the value of this W star and B star. Then if you get those two values, that can give you the unique points which will actually satisfy this equation what we have, which will be the support vectors of that particular equation or curve that we have. So for that, what we do, we have to differentiate this Lagrange's equation, which is lambda, which can be written in terms of L of W, B, and lambda. This is the Lagrange's inequalities or equalities we call, which is equal to half transpose into W plus sigma equal to 1 to n if there are n data points, lambda I into 1 minus Ti Twi transpose Xi plus B. This is like Lagrange's equation. Now this equation should be solved. This is my fourth equation, say. Now this equation, if you want, what we do is we have to find the minimum value. So to find the minimum value, what we do, we have to differentiate this equation with respect to W once and with respect to B once, so that we get W star value and B star value. In order to get these two values, we have to differentiate this equation once with W and once with B. We differentiate with respect to W and B. So if you differentiate, that is dou, how do we write, dou L by dou W, like that we have to write, or we can write it as delta with respect to W of L. This is how we write. If you differentiate this equation, we actually get W minus, because we are differentiating with respect to W, one W will go minus sigma, because lambda is, we are differentiating with respect to W, so lambda means it's a constant, so it will become 0, it will I'm expanding this and then doing it, so it will become anyhow 0. So I'm just ignoring that other terms and directly writing the expression as lambda I ti xi, because w, with respect to w I'm doing, so this term will go, so we'll have only these terms and remaining terms will become 0. And this sigma is between I equal to 1 to n. So now you have we have differentiated with respect to w. Similarly, we have to differentiate the same equation with respect to b, which is dou L by dou b. Dou L by dou b. If you do it, then this first term will become, we don't have a b term, so that will become 0. So again, in the second expanded term, we have only the last b term is there. So it will be minus sigma I equal to 1 to that lambda I ti. This is the second value that we have. When we differentiate with respect to w, you will get one value, and with respect to b, when you differentiate, you get the other value. Now what we have to do is we have to set these two values to 0 and find the values for w star and b star. If that w and so now if you equate these two terms to 0 and then find the values, your w star will be, from the first equation we'll get w star value sigma I equal to 1 to n lambda I ti xi, and the second term, this one, it will be sigma I equal to 1 to n lambda I ti equal to 0. So these are the two values. Now substitute these two values in our original Lagrange's equation, that is the fourth equation. If you substitute, then the values will be, wherever you have w, means now we found the values for, so that will be L of w star comma b star comma lambda is what we are finding out, which is equal to sigma I equal to 1 to n lambda I minus sigma I equal to 1 to n lambda I ti minus half sigma I equal to 1 to n. Another term will be there, which is j equal to 1 to n lambda I lambda j ti, because there is already one lambda here in this equation. In this equation, we already have a lambda I value, isn't it? So I'm taking, now in my equation, I got another lambda. Instead of getting confused, there are two different lambda I, and the other one is with respect to j. So that's the reason why I have taken one as lambda I and other as lambda j, and then ti tj xi transpose into xj. So this is the equation that we have. Now this equation, or this is known as a dual problem. It's called as a dual problem. This is called dual problem. And now we have to find the maximum with respect to lambda I. What is the maximum value we have to find? The constraints are, one is lambda I is greater than or equal to 0, and the other constraint is sigma I equal to 1 to n lambda I ti equal to 0. For these two constraints, we have to find the solution for the, in the above Lagrange's equation, you have to substitute and find the solutions. So for which, for the support vector equation, what is the support vector equation? Where it is equal to T of, the support vector equation is T of W transpose xi plus b is equal to 1. For if you are thinking that your hyperplane is this, then to get the support vectors, we have to substitute these and then find the values which are having the So for which, from when you substitute these values and find, it will be B star. B star value, what the support vector values will be, B star is equal to 1 by ns sigma for all the support vectors that are represented with j. The values are tj minus sigma t equal to 1 to n lambda I ti xi transpose xj, and the other one w star is equal to w star transpose some, instead of x I'm writing it as z, because again in the equation I also already have a x, so plus b star. So substitute in this, so which is equal to sigma I equal to 1 to n lambda I ti xi, this whole transpose into z plus b star. So this is the equation. And now if to classify if you are asked to find a new data point is given and asked if it is belong to which class it is falling, then you have to substitute in this and find the values. This is how they find out whether a given data point is, a new data point is given, then how to calculate is we substitute in this. We'll do a problem on it, then you will understand. We'll substitute the values and show you how we can decide like which class they belong. Here we are taking, here whatever we have discussed, that hyperplane, and then finding the parallel lines, parallel hyperplanes, and then saying into which class they're belonging and all. Here we have not considered the error part. We are assuming that we don't have any, means there is no misclassification of any data points. So this is how we have calculated. But in reality, if you see, there will be always, and we are assuming this is a linearly separable data. So we took it as a straight line. That's why we took it as T transpose x plus b equal to 0 and all, we have done it. But in reality, if you see, in real world practical situations, it is always a non-linearly separable data only will be coming across. So in that case, if it is non-linearly separable data, there will be some misclassifications. That means you have an error, which we call it as noise, isn't it? In that constraint, those we have to include an error part to these equations, whatever we have calculated. That error part we call, that mismatch, there can be two mismatches. One, which is wrongly classified, is one, like class A being the data point is there in class B, that is misclassified, that is one category. Another one is there may be data points which fall in between these data, between the two hyperplanes. We had a hyperplane like this, and we had two hyperplanes this side and this side. We may have the new data point may fall somewhere here. Then the distance, this distance is a error, isn't it? So that also we have to calculate. So there can be two types of errors. So that errors, or you can call it as a noise also, it can be. So that, how do you introduce into these equations and then calculate? In that case, we introduce a parameter called as a eta. We assume which is always greater than or equal to 0. This is what we consider, and we introduce this, and this eta is called as a slack variable. It is called as slack variable. In non-linear or a real-time data where there is non-linearly separable data set, then we introduce a new term called a slack variable. So wherever we have taken it as the equation which we have taken previously was equal to 0 or equal to 1. Now instead of 1, we will take the noise also we have to include, because it's an error. We have to subtract it from the equation. So we are writing it as, we write the equation now as like this. Greater than or equal to 1 previously we wrote, minus this eta I. Why we are calling eta I? That can be, you can have more than one error value. So that's the reason why we are taking, this is called, this parameter or this variable is called as a slack variable. Now for this equation, like how in the previous case we have calculated W star value and B star value, same way we have to find the minimum value for minimum no, for a minimum error value. We have to find the width of it, or what is the equation for that. We have to, for that we have to, this is again a minimization problem. So minimization problem. So minimize, which equation is W star dot W plus C in Cx is what we write a constant C instead of this eta. We replace it with a term called C. C is it's a trade-off parameter, we say, that decides how much weight to be added on each of these data points, so that we get nullified by the error term that we have. So this is a trade-off parameter which is represented by C. This in the now this equation should be minimized. That is what we are trying to identify. Say same like how we have written the Lagrange's equation. Now it will be Lagrange's equation in terms of weight and this error term, which we call it as a sigma or epsilon, some noise parameter. So which is equal to W transpose T plus C plus the trade-off C. And now I'm having many more than one noise parameter, isn't it? So 1 to n some epsilon I, where epsilon I is the error term that we are having. So how this now for this condition, again we have to apply that KK conditions, KKT conditions, and then we have to solve for W star and B star. Now the conditions will slightly change with lambda I star into 1 minus Ti into W star transpose into Xi plus B star minus, previously we closed this equation here itself in the case of when I didn't consider the noise term, but now since we are considering the noise term, we have to include even the slack variable, which is minus eta. Where is the point? Minus eta is equal to 0. This is the first equation, and the second equation will be C minus lambda I star into eta I is equal to 0. That's the second equation. And third equation will be sigma equal to 1 to n lambda I star into Ti equal to 0. This is the third equation. So solving these three equations, then again we will get, we have to solve for W star and B star, like taking the derivatives and all, how we have done previously. And then we will get for the noise with the noise term or the error term considered in the non-linearly separable data. All these derivations is a little mathematically complicated, so we are not going into the details. I'm just writing the equations only to some extent. We are not writing the complete derivation. You will not find in your textbooks also this complete derivation. So he has only spoken about the representations what I have given. The first one where we didn't consider the slack variables, it is called as a hard margin. The distance or the gap what we have, we call it as a hard margin. When we are considering the noise terms, we call it as a soft margin. Here when it is a soft margin, we consider even the noise term. So that's the reason why we call it as a soft margin. And there it is restricted. We don't consider the errors. So we call it as a hard margin. Of all this, there is one more thing. We have something called an important term that we usually come across in SVMs. We call something called as a kernel trick. We have something called as kernel trick. What is this kernel trick? CK. what is kernel trick is, till now we have taken all linearly separable data. When it is linearly separable data, we don't have any issue. When it is non-linearly separable data, we have a problem of, say for example, the number of dimensions, or we can say, if we are using more dimensions, then we might be able to solve linearly, that linear, we can find the linear decision boundary and then separate the classes. To derive that means, say for example, to explain this more easily, say for example, you're having some data points, say like this. You have one type of class like this and another type of data points like this around this. Usually in our real world practical situations, you have data points like this. So when you are having one class like this and the other class of data points around that, now can we linearly separate these data? Can we do that? We cannot do using a single line. We have to go for a curve. If you map this, usually what we do is we project it onto a lower dimensions and try to solve or separate the data. So if you try to map the data points onto, this is a two-dimensional data, isn't it? Now I'm trying to put it onto a one-dimensional data, that is a line, and see how the data points are. In this case also, you will find that all your data points of one class are here and the other are here. So can we separate these data points? We cannot do when you use dimensionality reduction or all. Will not be able to solve or classify the data when it is real world data, when you have something like this. So we have to go for a higher dimensional data. Say for that, what we do is we use something called as a kernel trick. What is this kernel trick is, we map some the data which is like in terms of x and y coordinates, x coordinate and y coordinates, we move on to a higher dimension. Means a three-dimensional dimensions we move, or we map the two-dimensional data into a three-dimensional data, and then try to see the same data. If you represent using a three-dimensional space, then maybe your all your data points here and the other data points may be somewhere little above the original where you have all your cross points. So this is possible. How? When it is possible, when you're looking at a xy coordinates, you're not able to locate the data points. When you moved onto a three-dimensional space, when you have x, y and z coordinates, you are able to see that they can be separated by a plane in between. Like I gave you in your first class when I explained this, the same concept I explained using a water fish tank. If you look into the fish tank from the top view, or when you look at the fish tank from the front, you feel that all the fishes are in the same plane. All the types of fishes are in the same plane when you look from the front, but you cannot separate them. But the same fishes, when you look from the top view, what happens? When you're looking from the top view, you are actually looking into the depth also. So x coordinate, y coordinate and the z coordinate, all the three coordinates, instead of looking only x and y coordinate, when you look from the top, you have three coordinates. And when you're looking from three-dimensional data, you can see that the fish of different colors are at different levels, and you can separate them using a hyperplane between them. That is what is a kernel trick. When you are when there is nonlinear data and you are not able to separate them using a straight line, then what we do is we apply a kernel trick. Means we map the lower dimensional data onto a higher dimensional space, so that we can then able to separate them or categorize them into different categories. That's what we do in kernel trick. This is an important one, sir. What is a kernel trick, or how do you apply a kernel trick in SVM is mostly asked. So you should remember that in a kernel trick, we map lower dimensional data into a higher dimensional space. Lower dimensional space to higher dimensional space we move. That means instead of x coordinate and y coordinate, we are moving into x, y and z coordinate. This is 2-dimensional and this is 3-dimensional. So it is not, I took an example like this. It can be more than this also possible. So how do you represent is, we represent using different kernels. What are the different kernels possible? Kernel functions that are that we can use are, basically we can use polynomial kernels, or we can use uh, sigmoid functions and other kernel functions that are available. There are about sigmoid function or a kernel polynomial function. 1 minute, I'll write the equations of those kernels. Here, polynomial kernel can be written as k of x comma y. X comma y can be written as 1 plus x transpose y, where it is power of s. Where s is equal to 1, this will become a linear kernel. When the degree of s is more, like 2 or 3, then this becomes a polynomial kernel. And the sigmoid function can also be used as a kernel function. So if it is a kernel function of sigmoid type, then the equation will be tan h of k x transpose y minus some delta. This is how we write the sigmoid function. And then another kernel function is radial basis kernel function, which is k of x comma y, which can be written as e to the power of minus 1 by 2 sigma square into x minus y whole square. So this is for the radial Bayesian function. So these are the basic kernel functions that are usually used in terms of when you're in the kernel trick. So what we basically do is we transform the lower dimensional data into higher dimensional space. Remember that what is a kernel trick, or what do you do is, means how do you solve this is, wherever in that equation we have xi, we'll replace with phi of xi. Wherever you have yi, you will replace it with phi of yi. What is this phi means? Based on which function you are applying. If it is a polynomial function, then you will write this polynomial equation. If you are writing sigmoid function, then you will use this function. Or if it is a radial Bayesian function, then instead of wherever you find x and y, you will substitute this function. This we solve instead of expanding the expression and then solving. In the kernel trick, we don't expand the functions. We just substitute the values and find the value or evaluate it. We don't expand the functions. If you expand the function, obviously the time complexity will increase. So in order to avoid that time complexity, what we do is that not time, computational cost will increase. So in order to reduce the computational cost, we just substitute the value, these functions, and find the values of those functions. So with that, we don't increase the computational costs. So that is what is about the kernel trick. This is how you solve if it is a binary classification. What if we are having, can we do this classification? If it is a multi-class classification, can we apply SVM is another question. Till now, whatever we discussed, we were discussing only in terms of x and y coordinates. Only binary, plus class and a negative class, means binary classification only we discussed. Binary classification. What about if it is a multi-class classification? Then can we apply SVM on multi-class classification? Yes, we can apply SVM algorithm on a multi-class classification also. If it is a multi-class classification, how do we do? Here we are only talking about one hyperplane, which is dividing the data points into two classes, isn't it? So then how do you do if it is a multi-class? Simple. We take, if there are another type called minus data points also on this side. So we again put these all into one class, and this as one class. And then we try to find the hyperplane to classify these two. And once we classify this as one class and this as one class, now again we will take this class and again then we try to identify another hyperplane to classify them into two classes. This is what we do in a multi-class classification. So SVMs can be also used for a multi-class classification purpose also. So this is about SVM. There's lots of mathematical equations that you should remember. Usually in your exam, what they ask is, they will ask you to solve, problems are also possible in SVM. The only problem that is possible in SVM is he will ask you to find the W star and B star value, or find the hyperplane equation. He will ask. He will give you the class 1 and class 2 data points, and then he will ask you to find the equation, that is the hyperplane that is separating these data points. So for that, what you have to do is, you have to, let me write one example so that you will come to know how it will be. Now class 1 is having the points like 1 1 1 2 2 1, and there is another class 0 0 1 0. These are the data points coordinates that they are given. This is one class and this is the second class. This is class 1 and this is class 2. Now he's asking us to identify a hyperplane which actually separates these two classes. So you can draw a graph and plot all the points. Now the support vectors will be what? You can pick any points as your support vector. Since he has given here 3 sets of data points, I'm taking 3 support vectors. So let me write support vector 1 is how do you get the support vectors is, first plot these points onto a graph. So 0 0, I'm considering 0 1, this is my 0 0 point, this point. Next 1 0, 1 0 will be here, 1 0. Another point is another point is where 1 0 0 1 0 1 will be this side, so it will be 0 1. And then there is another point which is 1 1. So obviously your 1 1 will come where somewhere here. And then you have 1 2. So 1 and 2 somewhere here. And then 1 2. Okay, 2. And then you have another point as 2 1. 2 1 is somewhere here. Now what can be the hyperplane that is separating this is, first you have to identify the support vectors. I'm considering the first point, that is 0 1 as one support vector, 0 1 as one support vector, which I'm considering as S1, support vector S1. Another support vector S2 is 1 0, and another one is 1 1. These are the 3 support vectors I'm having. So, and the bias value usually he will give, because it's a hyper line, we are taking it as a 1. So now you have to consider bias as 1. So your support vectors will be rewritten as 0 1 1. S2 is equal to 1 0 1. I'm just including one more coordinate, that's all. 3 is 1 1 1. So these are the 3 support vectors that I'm having. Now for these 3 support vectors, we have to calculate that lambda, or here I'm usually, what in derivation what we did is, we found the lambda 1, lambda 2, lambda 3, like that we have written. We can write it in terms of alpha also. Now there are 3 support vectors, 3 equations you have to write. So alpha 1 S1 in S1, dot product of S1 into S1, alpha 2 S1 S2 S1 plus alpha 3 S3 S1 is equal to 1 is one equation. The other equation is alpha 1 S1 S2 plus alpha 2 S2 S2 plus alpha 3 is S2 S3 equal to plus 1, because the hyperplane will be one side, it will be, if I'm taking 1, the other side, one side it will be plus 1, the other side will be minus 1. So one equation I've taken as plus 1 and the other equation will be minus 1. So which will be alpha 1 S1 S3 plus alpha 2 S2 plus alpha 3 S3 S3 equal to minus 1. Now solving this, now these values you have to substitute S1 S2 S3 values. Now solving these three equations, you will get three simultaneous equations to be solved. You have to calculate the alpha 1 alpha 2 and alpha 3 values. Once you get that, then in our original equation, that is W value and the bias value you will get, B value and W value you will get. Once you solve, W value will be formula. Once you got alpha 1 alpha 2 alpha 3, your W value, how you will get W value is W is equal to sigma I equal to 1 to n alpha I Si. So just expand this, alpha I means alpha 1 S1 plus alpha 2 S2 alpha 3 S3. So substitute in that and then identify what is the W value. You will get a three dimension, like some three rows values you will get. The last one will be the bias value and the remaining two will be the X and Y coordinates. Now using this, write the equation for the line equation, which will be y is equal to mx plus b, isn't it? So in this, you substitute those values, you will get the line equation. That's how you solve the SVM. Like in your prescribed textbook, there are two exercise problems. Please try to solve them using this method. I think first problem is what I have actually written here. The same problem is there in your textbook. Please try to solve these two problems. Exam also you may get a problem on SVM. Or he will ask the algorithm of SVM, or he may ask you to derive that width, what is the maximum width of the margin, that 2 by mod W, that he may ask. Or another one possible, what are slack value, slack, short answers you will get, what are slack variables, or what is KKT constraints, such questions you will get. Another important question that is possible from this is kernel trick. Most of the if you have studied machine learning, if you have studied SVM, they will ask what is kernel trick. So that's another important concept that you should remember. This is all about SVM. There's nothing more than this in any textbook. If you see, these are the only things you will find. I don't know how many of you actually followed what I discussed. Hope at least a few topics which I spoke, you understood, I assume. Sir?
Yes, ma'am, we understood.
Please go through that textbook, your prescribed textbook, and see one chapter. The whole chapter is about SVM. Chapter 8 is about SVM. SVM is the most popular and important topic. So please go through it. Once again, go try to read it, then you will understand what I spoke in today's class. So then, there are little vague things. How did this equation come and all? The background is actually mathematics. KKT constraints, Lagrangian multipliers, all these convex problem solving, all these are the ones which you usually find in maths. Optimization problems or multivariable solving optimization problems. If you have an idea in mathematics, you will find these equations in there, and then you can link those things to this particular concept. That's all I want to talk about today's class. Anything else you want? Tell me, sir.
మేడం అక్కడ XY కోఆర్డినేట్స్ జెడ్ డైమెన్షన్ పెట్టాలి కదా, అక్కడ జెడ్ డైమెన్షన్ ఎలా వస్తుంది?
లేదు
But
సార్,
I have only two
డైమెన్షన్ రాదు
dimensions.
సార్. ఇప్పుడు XY కోఆర్డినేట్ లో ఒక పాయింట్ ఉంది, సే 1,1 అనే పాయింట్ ఉంది XY కోఆర్డినేట్ లో. దాన్నే మనము 3 డైమెన్షనల్ లో అయితే ఎట్లా రిప్రజెంట్ చేస్తాము? దానికి ఇంకొక కోఆర్డినేట్
జెడ్ ఐ నీడ్ టు యాడ్, రైట్? జెడ్ ఐ నీడ్ టు యాడ్. హౌ ఆ జెడ్ వాల్యూ ఎలా యాడ్ అవుతుంది?
సార్ అదే సార్ ఇప్పుడు చెప్తుంది, అదే నేను చెప్తున్నాను. ఇప్పుడు మీకు XY కోఆర్డినేట్ ఉంది, అందుకనే దాన్ని ఎక్స్పాండ్ చేయము మీరు కర్నల్ ఫంక్షన్స్ లో. దట్స్ వాట్ ఐఎమ్ సేయింగ్. ఏది పాయింట్ క్లోజ్ చేశాను. మీరు ఆ పాయింట్స్ తీసుకున్నప్పుడు ఇదే కదా మీరు అడుగుతున్నారు, కర్నల్ ట్రిక్ లోనే కదా. ఇది XY కోఆర్డినేట్స్ లో పాయింట్స్ ఇట్లా ఉన్నాయి సార్. ఇవే పాయింట్స్ ని ఇమాజిన్, సే ఫర్ ఎగ్జాంపుల్ ఇమాజిన్ ద సేమ్ పాయింట్స్ లైక్ రూమ్ కార్నర్ తీసుకోండి. ఒక రూమ్ కార్నర్ తీసుకుంటే ఈ డాట్స్ అన్ని కూడా కిందికి ఉన్నాయి, ఈ కిందన ఉన్నాయి. ఈ క్రాస్ మార్క్స్ ఏవైతే ఉన్నాయో అవి పైన ఉన్నాయి. ఐఎమ్ ట్రైంగ్ టు డ్రా 3 డైమెన్షనల్ ఇమేజ్. సో అప్పుడు ఏమవుతుంది, ఇక్కడ మధ్యలో మీకు ఒక ప్లేన్ గీయచ్చు కదా, విచ్ యాక్చువల్లీ సపరేట్స్ దీస్ పాయింట్స్. పైన అంటే ఒక మధ్యలో ఒక పేపర్ పెట్టారనుకోండి, దట్ ఈస్ వాట్ ఈస్ ద కర్నల్ ట్రిక్. వీఆర్ ట్రైంగ్ టు ఐడెంటిఫై దిస్ ప్లేన్ విచ్ యాక్చువల్లీ సపరేట్స్ ద పాయింట్స్ ఆన్ ద అదర్ సైడ్ అండ్ ద పాయింట్స్ ఆన్ దిస్ సైడ్. How is it possible when ఈ XY coordinates ని instead of XY you're showing it on a 3 dimensional? ఇందాక మీకు అక్కడ ప్రాబ్లం లో కూడా మీకు 1 పాయింట్ ఉంది, దీన్ని 3 డైమెన్షన్ లో చూపించినప్పుడు బయాస్ అనేది ఒకటి యాడ్ చేసి నేను ఇట్లా చూపించా, Z కోఆర్డినేట్ ఒకటి చూపించా కదా, ఇంకొక పాయింట్ యాడ్ అవుతుంది XY. దానిని మనం ఎట్లా చేస్తున్నాం అంటే, మీరు మామూలుగా రిప్రజెంట్ చేసినప్పుడు XY రిప్రజెంట్ చేస్తున్నారు, ఇన్స్టెడ్ ఆఫ్ phi of x అండ్ phi of y అని రిప్రజెంట్ చేస్తాం. ఈ phi ఏంటి అంటే అవి కర్నల్ ఫంక్షన్. ఇన్స్టెడ్ ఆఫ్ x, y considering it as phi of x and phi of y. వాట్ ఈస్ phi of x అంటే అది ఏ కర్నల్ తీసుకుంటున్నామో ఆ కర్నల్ సబ్స్టిట్యూట్ చేసేస్తాం. ఇప్పుడు పాలినామియల్ అనుకోండి, ఈ ఫంక్షన్ ని సబ్స్టిట్యూట్ చేసేస్తాం. ఇన్స్టెడ్ ఆఫ్ ఎక్స్ ప్లేస్ లో వేరెవర్ ఎక్స్ ఈస్ కమింగ్, ఐ విల్ సబ్స్టిట్యూట్ దిస్ హోల్ ఫంక్షన్. అందుకనే అది ఎక్స్పాండ్ చేయను, జస్ట్ ఆ ఫంక్షన్ సబ్స్టిట్యూట్ చేస్తాను. ఎక్స్పాండ్ చేస్తే మీరు మళ్ళీ అది సాల్వ్ చేయడానికి ఎక్స్పాండ్ చేయాలంటే ఎస్ బదులు 2 ఉంది అనుకోండి, క్వాడ్రాటిక్ ఈక్వేషన్ అంటే దాన్ని ఎక్స్పాండ్ చేస్తే మళ్ళీ మీకు టర్మ్స్ ఎక్కువైపోతాయి కదా, 4 టర్మ్స్ వస్తాయి. a స్క్వేర్ మైనస్ b స్క్వేర్ ఉంది, a స్క్వేర్ ప్లస్ b స్క్వేర్ ఉంది, ఇప్పుడు అందులో ఉంటాయి 3 టర్మ్స్ అయిపోయినాయి, పెరిగిపోయింది కదా కాంప్లెక్సిటీ సాల్వ్ చేయడానికి. సో అట్లా పెరగకుండా చేయాలి అంటే జస్ట్ ఈ ఫంక్షన్ తీసుకుంటాను, ఈ ఫంక్షన్ కన్సిడర్ చేస్తాను, కానీ ఈ ఎక్స్ వాల్యూ వై వాల్యూ మాత్రమే సబ్స్టిట్యూట్ చేసి ఈ ఫంక్షన్ తాలూకా వాల్యూ కనుక్కుంటా. సో అప్పుడు ఏమైంది, మీరు ఎక్స్పాండ్ చేయట్లేదు కాబట్టి కాంప్లెక్సిటీ పెరగదు, కంప్యూటేషనల్ కాంప్లెక్సిటీ పెరగదు. ఈ ఫంక్షన్ ని నేను phi అని రిప్రజెంట్ చేస్తున్నా. అర్థమైందా సార్?
ఓకే మేడం,
నాకు తెలుసు దెర్ ఈస్ అ కన్ఫ్యూజన్, ఇట్ ఈస్ నాట్ క్లియర్. వన్స్ గో త్రూ ద టెక్స్ట్ బుక్, maybe the way I'm explaining, and one more thing, you are not seeing me, so adi oka major drawback. I'm not able to identify how many. I know I feel everybody is blank with this topic. ఎందుకు క్వశ్చన్ గొడవ SVM అని అనుకుంటే స్టేజ్ లో ఉండుంటారని నేను అనుకుంటున్నా. కరెక్టేనా సార్?
Since there are multiple equations that we need to understand where is the point.
Yes sir, that is not possible unless you go through personal గా మీరు చదివితే. అందులో ఒక 10 pages 15 pages ఉన్నాయి సార్ ఆ చాప్టర్. వన్స్ యూ రీడ్, గివ్ ఎ రీడింగ్, then you recollect what I spoke, you can link it, then you will understand. just listening to me, you will feel like it's Greek and Latin. What is this equations? Where from she brought all this? Yes, obviously you'll feel it. But once you give a reading now, after we close the class, don't wait for tomorrow. Please read it today itself. That 5-10 pages, whatever is there, you please read. At least if you're not able to read the whole chapter, please read the first few topics till the slack variables. If you read, that will be sufficient. You will get some idea. Kernel trick అనేది it's just a small topic, like ఇంకొక పేజ్ ఉంటుంది అది అంతే. సో అది ఈజీగా మీకు అర్థమైపోతుంది. ఆ ముందు అర్థమైతే ఇది ఈజీగా అర్థమవుతుంది. లోవర్ డైమెన్షనల్ లో డేటాని హైయర్ డైమెన్షనల్ లో చూపిస్తాం అంతే. సేమ్ డేటా. సార్ ఫర్ ఎగ్జాంపుల్ ఇప్పుడు మామూలుగా మనం మూవీ చూస్తాం. మూవీ చూసినప్పుడు అది 2 డైమెన్షనల్ లోనే కదా చూస్తున్నాము. స్క్రీన్ మీకు 2 డైమెన్షనల్ లోనే ఉంది కదా, XY ఉంది. అదే 3D ఇమేజ్ అయితే 3D మూవీస్ చూస్తున్నారు. Still they're projecting the 3D image on a 2D screen only కదా. అవునా కదా సార్? మీరు ఆ గ్లాసెస్ వేసుకున్నప్పుడే మీకు ఆ 3rd డైమెన్షన్ కనిపిస్తుంది. The same thing we are telling here, ఆ 2D ఇమేజ్ 2D లో ఉన్నప్పుడు వీఆర్ నాట్ ఏబుల్ టు ఫైండ్ దట్ ఆ సపరేషన్ చేయడానికి వీలు కాదు. సో అందుకని ఇంకొక డైమెన్షన్ ప్రొజెక్ట్ చేసి అప్పుడు మధ్యలో ఒక స్పేస్ క్రియేట్ చేస్తున్నాం. అప్పుడు మధ్యలో స్పేస్ వచ్చింది కాబట్టి 3 డైమెన్షన్ లో వచ్చింది కాబట్టి అక్కడ ఒక మధ్యలో ఒక ప్లేన్ ఉంది. సో ఆ ప్లేన్ కి అటుపక్క ఉన్నది ఒక క్లాసు, ఇటుపక్క ఉన్నది ఇంకో క్లాసు అని చెప్తున్నాం. ఇప్పుడు అక్కడ మనం ఏమైనా 3D ఇమేజ్ లో మనం ఏమైనా ఇది చేసామా? ఏమి చేయలేదు. డిడ్ వి డూ ఎనీథింగ్? ఆ 3D ఇమేజ్ చూపించడానికి 2D మీరు గ్లాసెస్ తీస్తే అది 2D ఇమేజ్ లాగే కనిపిస్తుంది కదా. అవునా సార్? 3D ఇమేజ్ అయినా మీరు కళ్ళజోడు తీసి చూసారు అనుకోండి, అది 2D ఇమేజ్ లా
బట్ అక్కడ ఆ ఎగ్జాంపుల్ లో వీడియో తీసేటప్పుడు మాత్రం 3D లోనే తీయాలి కదా, 3D కనిపించాలి.
ఎస్ సార్, అక్కడ అదే చేస్తున్నాము. మనం ఏం చేస్తున్నాం ఇక్కడ, ఆ ఇల్యూషన్ చేయడం కోసం అని చెప్పి ఇక్కడ మనం అట్లా అది అంటే అట్లా చేసి అట్లా మ్యాప్ చేస్తున్నాము అని ఇమాజిన్ చేసుకొని అక్కడ ఒక ప్లేన్ ఉంది అని ఇమాజిన్ చేస్తున్నాము. అదే చెప్తున్నాను నేను.
You want to say that this is an imaginary plane, but we are not building again.
We are not doing anything. We are just అదే పాయింట్ ని ఇంకొక స్పేస్ డైమెన్షన్ ఉంది అని ఇమాజిన్ చేసి అక్కడ మధ్యలో ఒక ప్లేన్ గీస్తున్నాం.
ఓకే,
ఒకసారి మీరు వన్స్ గివ్ ఎ రీడింగ్ ఆఫ్ దట్ 10 pages ఎంత 169 నుంచి 179 వరకు ఒక 10 pages సార్. ఆ 10 pages చదివితే మీకు చాలా క్లియర్ గా ఉంటుంది. వన్ 169 నుంచి 179 వరకు ఉన్న ఆ పేజెస్ మాత్రం చదవండి SVM గురించి. యూ విల్ బి క్లియర్. నేను అక్కడ ఏ టాపిక్ స్కిప్ కొట్టలేదు. ఆ SVM టాపిక్ యాక్చువల్లీ SVM ఈజ్ మై ఫేవరెట్ టాపిక్. కానీ అది మీకు అర్థం చేయడానికి ఇట్ విల్ టేక్ టైం. మీరు ఒక రీడింగ్ ఇస్తే మీకు క్లియర్ అవుతుంది. జస్ట్ గివ్ వన్ రీడింగ్. ఓకే
ఓకే మేడం, థ్యాంక్ యూ.
Okay, sir. Again, we will anyhow, if possible, we'll again discuss about this. Again, if you want, I can revisit this topic at later point of time. Okay. ఈ వారంలో ఇంకొక రోజు తీసుకుంటా సార్, ఇంకో క్లాస్ ఆన్లైన్ లోనే తీసుకుంటా. బట్ ఇంకొక రోజు తీసుకుంటా, అది ఎప్పుడు అనేది నేను కన్ఫర్మ్ చేస్తాను. ఇఫ్ నాట్ పాసిబుల్, ఐ విల్ టేక్ ఆన్ ఎ వీకెండ్. బట్ 1 hour క్లాస్ అయితే ఇంకో క్లాస్ అయితే కంపల్సరీ తీసుకుంటా.
ఓకే మేడం.
ఐ కన్ఫర్మ్ విచ్ డే ఐఎమ్ టేకింగ్. నాకు యాక్చువల్లీ మాట్లాడుతున్న కొద్ది కాఫ్ వస్తుంది. ఐఎమ్ కంట్రోలింగ్ మై సెల్ఫ్ అండ్ టాకింగ్. సో అందుకని ఇక్కడికే స్టాప్ చేసిన. అండ్ ఐ నో దిస్ ఈజ్ ఆల్ కొంచెం హెఫ్టిక్ గా అనిపించి ఉండొచ్చు. అందుకనే ఇంకో నెక్స్ట్ టాపిక్ చెప్తే మీకు మళ్ళీ కష్టం అవుతుంది. సో అందుకని నేను ఇంకే ముందుకు వెళ్ళట్లేదు. అందుకని ఇంకొక క్లాస్ తీసుకుంటా, అది ఇంకొక రోజు చెప్తాను. బట్ బిఫోర్ దట్ నెక్స్ట్ క్లాస్, ప్లీజ్ గివ్ అ రీడింగ్ అబౌట్ ద SVM. Okay, and I didn't talk about SVR, that is support vector regression. Since it's not there in, so adi kuda support vector regression ga kuda vaadachu, but I'm not touching it anywhere because it's more popular for classification purpose. Adi oka small para undi అందులో textbook lo. If you want, you can go through it. But remember, it is also used as for, it can be used for both regression as well as for classification, but it's more popular as a classification algorithm. Okay. ఫస్ట్ బేసిక్ టర్మినాలజీ అవన్నీ అర్థం చేసుకోండి, అదే మీకు సఫిషియంట్. ఆ కర్నల్ ట్రిక్ ఒకటి అర్థం చేసుకోవాలి, అది ఒకటి ఇంపార్టెంట్. మిగతా ఈక్వేషన్స్, పీపుల్ హూ ఆర్ ఫెమిలియర్ విత్ మ్యాథమెటిక్స్, ప్లీజ్ గో త్రూ దట్ mathematics behind. If you're not familiar, just leave that.
ఎగ్జామ్ లో మ్యాథమెటిక్స్ ఇస్తారు మేడం. అది
డెరివేషన్స్ ఇవ్వకపోవచ్చు సార్, నేను పేపర్ సెట్ చేస్తే నేను ఇయ్యను సార్, ఎందుకంటే అది అందరికీ అర్థం కాదు.
ప్రీవియస్ ఎప్పుడైనా ఇచ్చారా మీరు? ఇవ్వకపోయినా కానీ
బీటెక్ లెవెల్లో ఇచ్చారు సార్, కానీ మీ పేపర్స్ లో లేదు. మీ పేపర్స్ లో ఓన్లీ థియరిటికల్ ఇవే ఉన్నాయి.
ఓకే మేడం.
సో ఆ టర్మినాలజీ, మార్జిన్ ఎట్లా సెలెక్ట్ చేస్తాము అట్లాంటివన్నీ చూడండి. కర్నల్ ట్రిక్ అంటే ఏంటి అన్నది కంపల్సరీ చూడండి. అది ఎక్కడికి వెళ్ళినా మీరు రేపు ప్రాజెక్ట్స్ చేసినా ఎక్కడ చేసినా ఎంఎల్ చదువుకున్నారు అంటే వాట్ ఈస్ అ కర్నల్ ట్రిక్ అని అడుగుతారు. సో అందుకని అది కంపల్సరీ, ఆ డెఫినేషన్ అయితే చూడండి కంపల్సరీ. డెఫినేషన్ సింపుల్ సార్, లోవర్ డైమెన్షనల్ స్పేస్ నుంచి హైయర్ డైమెన్షనల్ స్పేస్ లో రిప్రజెంట్ చేస్తాం అంతే. దట్ ఈస్ వాట్ ఈస్ అ కర్నల్ ట్రిక్. బికాస్ లోవర్ డైమెన్షనల్ లో మనం సపరేట్ చేయలేకపోతున్నాం కాబట్టి వీఆర్ నాట్ ఏబుల్ టు ఐడెంటిఫై ద డేటా బికాస్ ఇట్ ఈస్ నాన్ లీనియర్ డేటా. వి మూవ్ ఇట్ ఇంటూ హైయర్ డైమెన్షనల్ స్పేస్ అండ్ వి సపరేట్ ద డేటా. దట్స్ ఆల్ ఈస్ వాట్ ఈస్ కర్నల్ ట్రిక్. అది ట్రిక్. మీరు 2D ఇమేజ్ 3D ఇమేజ్ ఆ ట్రిక్ ఏముందో దీన్ని కూడా అదే అంటున్నాం, కర్నల్ ట్రిక్ అంటాం. ఓకే సార్, షల్ వి క్లోజ్ హియర్?
ఓకే మేడం, థ్యాంక్ యూ.
ఓకే సార్, ఓకే, గుడ్ నైట్ సార్. ఐ విల్ ఎండ్ హియర్.
గుడ్ నైట్ మేడం.
గుడ్ నైట్.